No, nothing happened. Everything's fine.
Yeah, everything is all right. Yeah.
Oh, okay, good.
Yeah. Okay. So we'd like to introduce our speaker, Peter Koltai, who'll be talking about coarse graining and manipulation of transport in non-autonomous systems.
Thank you very much. Let me see whether I can share here everything properly. All right. This should now be full screen, right? You can see my slides, I presume?
Yes.
Okay, so many thanks for having me. It is a pleasure and an honor. This is joint work with a couple of people, Gary Freuland and Han Li and Martin Stahn from Potsdam. Let's see, is this working? All right, so I would like to start with some illustration of what kind of problems I'm considering. It's going to be transport, and I realized that this movie is going to be maybe a little bit cheesy for this audience, but yeah, sorry for that, and give me some feedback afterwards. Please let me know if you don't hear the audio of the video.
Check this out. I'm just gonna drag this plate through the water in the pool. That's it. But look what forms. Perfect black circles on the bottom of the pool. And it's so weird. They don't die. They just keep going right next to each other. I sped this footage up because the circles took 3 minutes to cross the pool and didn't seem to be dying out. These got sharper as they went and made it all the way across. Put a little food coloring into the ends. The food coloring travels from one end to the other and you can see the entire half ring. So cool. We just...
All right, so the main point is what she showed at the end, that when she puts this food coloring, this some kind of a material into this structure in the pool, which she generated, this doesn't disperse the food coloring, it keeps whatever is inside, and might move this around or with respect to the surrounding water mass, but it doesn't exchange mass. So these things are then most predictable if we suppose that the water motion around can be a little complicated and turbulent, and that's why these sets, these material or coherent sets in water are so important. And of course, one thing is playing in the pool, but we can scale things up, and you know, these objects, these structures appear also on large scale in the atmosphere, in the ocean, and they can have a large impact on our climate, weather, and so on and so on. So, for instance, these so-called Agulhas rings are very famous examples of these coherent sets. So this is what I would like to tune in to in my talk, and just, of course, to give credit to the giants of whom the shoulders I'm standing on. There are different views how to approach this problem of transport. There are more geometric views, that's kind of the left-hand side of the picture, where we are talking about transport barriers. You've heard about Lagrangian structures like finite-time, Lyapunov exponents, and also more recent concepts. And there is also less barrier, less codimension one geometric view on this issue, a more set-oriented or set-based view, where we are looking at persistent sets, and you have perhaps heard this in terms of almost invariance, metastability, and also coherence, what I'm going to talk about. And I gave you some names here who contributed to this, but it is definitely a very non-exhaustive list. How does the math look like? Let us start with the autonomous version of things. Here I suppose I have a ordinary differential equation in RD, of which the right-hand side is a velocity field v. It's autonomous at the beginning, giving rise to a one-parameter family of flows, this phi t. And now I can say that a subset of state space A is almost invariant, metastable, or persistent. These are now synonymous if with respect to some measure, how I want to measure things, most of A is mapped back to A after time t. Yeah, and this most of is now measured with respect to mu, and I take things relative to the original size of A. So if this ratio here is close to 1, I'm talking about an almost invariant set. And now I could talk about, okay, for which t, which times t, do I want this to be satisfied? But let's just brush these things under the rug. Yeah, go ahead, please.
Can we not brush this under the rug? Because what is close to 1? What do you mean?
Yeah, fair point. So you can, of course, have or consider different sets at this point, and you can ask, okay, what is, for example, maximizing this ratio for all sets for which mu A is 1/2, considering or assuming that mu is a probability measure, so mu of x is 1. And you can set a specific time scale t, which is somehow inherent to your problem, and set that as a proxy. So you can fix t and say, I want to have sets which have a minimum or an exact volume, this and that, such that they are almost invariant. So there are ways to make this more precise, and all these asides are going to be becoming precise on the way. So
Okay.
I will show theorems which make these things crisp. At this point, I'm only trying to give you intuition of what the problem I'm considering. But thank you for your question, and I forgot to mention at the beginning, feel free to interrupt me anytime. So I'm not particular about receiving questions at the end. Okay, so this is the autonomous picture. Somehow there is a non-mobile set which should keep stuff in it. How does the mobile version of it look like? If I have a non-autonomous dynamics, so my right-hand side depends on time explicitly, then I have a 2-parameter family of flows. So there's a starting time s and a terminal time t, which appear here. If I want to define my flow, and I cannot assume that things are going to stay at the same place where they kind of started, as you have seen in the pool example at the beginning. So I say I have a coherent pair whenever I have a set AS at starting time and another set AT at terminal time, such that most of AS is mapped to AT by the flow from S to T, right? So this is this ratio. Now, if we look at this for a while, we see that this is kind of a void definition, because whichever set A I take as starting set, if I push this forward to time t and take that as AT, then I get a perfectly coherent family for, as I said, whichever A I take. So this is definitely not what I want to have. There seems to be some kind of an ingredient missing, and this ingredient is robustness under diffusion. So let me motivate us again with a picture. Consider some flow. I'm not showing the flow, I'm just showing you what happens with two sets, a black and a gray at initial time under the flow, so after the flow to time t, terminal time. The black set stays circular and the gray stays, or it doesn't stay anything it looked like. It's filamented, it's torn apart a little bit by the flow. So we would like to consider the black as coherent and the gray not. And now to make this quantitative and more rigorous, how we want to differentiate between these two qualitative behaviors, we add a little bit of diffusion. This is what you see implemented by a couple of red dots here. I just take random points in the sets and I diffuse them, and you see that the black set keeps most of the diffuse points in it, while the gray doesn't, because the perimeter of the set grew by a huge amount. It became a thin structure, so noise has a really easy job to kick, small noise has an easy job of kicking out these things. It gets even more prominent if I pull everything back by the deterministic dynamics to initial time. Then you see stuff stayed inside in the black set at initial time, and the red points, the perturb points from the gray set have been dispersed all over the place. And this forward diffuse backward picture, which you see indicated by the arrows going forward and backward, and getting kind of something robust under this forward backward concatenated evolution. This is formalized in works of early works of Gary Froiland and co-workers on finite-time coherent pairs. I will allude to this here, but will set up a different theory in my talk. So why are we talking about these things? Well, the ultimate goal would be to coarse-grain the transport behavior of complicated dynamical systems. My goal in this talk is going to be much more humble, actually. It's gonna be trying to understand the similarities or the equivalences between coherence and almost invariance, between this concept of non-autonomous and the very same concept or the similar or analogous concept in the autonomous setting. At this point, I like to quote Poincaré because his statement here just drives the message home very nicely. It says poetry is the art of giving different names to the very same thing, but mathematics is acting the other way around. It is the art of giving the same name to different things. So we are asking what is really the same in these two supposedly definitions, what I gave you before, between the non-autonomous and the autonomous ones. Why are we so interested in? Well, because this is what mathematics does. It tries to connect things at a higher level. We would like to be able to transfer existing theory from one end to the other. The autonomous concept is quite well understood, while the non-autonomous is just being developed. We would like to be able to devise efficient numerical methods on the way. And what with this talk I would like to achieve is to extend things from the coherent pair, as I showed before, like initial and finite time, two sets, to a whole family, a continuously time parameterized coherent family of sets. So how is this going to happen? Well, the most obvious thing to connect something non-autonomous to something autonomous is this all implementation. Just add time as an explicit dependent variable, get something which is one dimension higher than your original state variable, and things turn out to be autonomous. So this is my augmented system. Space-time. Augmented variables are going to be boldface here. So this non-autonomous ODE with now an explicit parameter theta acting as surrogate for time is included, and this whole thing becomes a autonomous system with an autonomous velocity field V. This generates also an autonomous flow. I can make the same game with a whole family of sets. So I have a time parameterized family of sets in state space, a theta. Theta stands for time. Then I can build a so-called augmented set, the boldface A, which just concatenates the family like slice-wise into a space-time sausage, as shown here in this picture, where the time slices are now the state space subsets A theta. And our idea will be to connect coherence to almost invariances to exploit the equivalence that if I have a family of sets which is coherent, then it should be the same in a sense by the considerations which I was showing at the very top of this slide. It's the same as saying that under a slightly perturbed noisy flow, but augmented flow, the augmented set, this augmented sausage, is now almost invariant. So this is the agenda what I'm going to follow, and now I will try to formalize this. For starters, to make things simple, let me consider a right-hand side which is tau periodic. So it's somehow periodic with a finite period tau. Then I consider now the slight stochastic perturbation of my dynamics. So I have this non-autonomous system here on from the previous slide, but I add a little bit of stochastic perturbation. So epsilon is a small number, and this is now some Brownian forcing. Yeah, WT is a standard Wiener process, and I mean this in the Ito sense. This gives rise to an augmented process, xt, where theta is basically deterministic, but x is now a random variable. Then I will measure quantitatively coherence by escape rates. So I say that the escape rate of a family A theta is now measured by the exponential decay of probability that my spatial process, this xt, stays in my coherent family. So I'm looking at the probability that x stays in A at the given time for all times from S to sometimes T. As T now goes to infinity, this thing, of course, decays to 0, unless A is some trivial set, like, you know, the full state space that I will rule out. So this decays to 0, and I'm looking at the exponential decay. So I'm taking the logarithm 1 over t, and then t going to infinity. I put here the minus to have an escape rate, which is a positive or non-negative number. And I'm going to call a set coherent, a family of sets coherent, if its escape rate is close to 0. Again, subject to the restrictions or these additions, which I talked about before as answer to the question which came. This is how I'm going to quantify coherence. And, here's the tool kit I'm going to use, or one part of it, transfer operators. I would like to lift everything to the operator level and talk about the evolution operator, which gives me the forward evolution of densities under the dynamics. So if my starting random variable is f distributed, let's say, f is a density, then xt is distributed according to some other density, which is given by then the dynamics, and the mapping, which maps f to this final density, is described by the so-called transfer operator. This is a Markov operator. If you don't like to think of it operators, think of it as the generalization of a stochastic matrix. It's positive, or some call it non-negative. It's integral preserving, probability is not getting lost, and these two things make it a Markov operator, which makes it a contraction in L1. Also, this time parameterized family of operators is a operator semigroup, saying that if I go s plus t times forward in time, it is the same as applying the s transfer operator first, and then, or the t transfer operator first, and then the s transfer operator afterwards. But this only holds, of course, if my process is time homogeneous, like autonomous. So how do I now get back to coherent families? Again, as before, I mentioned I consider the augmented process now. That is a time homogeneous process. So in space-time, the associated transfer operator this is now boldface because it acts on space-time functions, is now one parameter semigroup, which by classical semigroup theory will tell me that it is described by just one operator, the whole time parameterized family, by the so-called generator, which basically says that this operator satisfies this equation in the proper sense, which would be in the sense of a Cauchy problem on the respective spaces. But really just think of it as if there were matrices at this point, then you would exactly know how to solve this equation. Then PT is the exponential of t times g. Of course, this is now in quotation marks because this equation doesn't hold exactly for operators. G is an infinite operator, so this exponential can not be built as it is, but has to be interpreted in the sense of semigroup theory, which formalizes this connection. But just let me not get there, because I would like to tell you other things, and I will not require this on this high level, how I'm introducing things. But as many of you probably know and suspect at this point, this generator is nothing else than the Fokker-Planck operator, or the Kolmogorov forward operator, associated with the stochastic differential equation, which can be now written in a time slice-wise setting. So because I'm in augmented space, I'm having a transport term in time, and I'm having the Fokker-Planck operator of the STE at time theta for the spatial derivatives. So it's second order in space, and it's first order in time, this operator. But now, how does this whole thing help me to characterize coherent families? Well, that's where we have a result. So assuming sufficient smoothness of the coefficients of the dynamics acting, then if I now have a eigenfunction of this augmented generator, so this augmented eigenfunction is now a space-time function, bold F, at some non-zero eigenvalue, kappa, then I can show, on the one hand, that all time slices of this augmented eigenfunction have zero spatial mean, so they have just as big positive as negative parts for every time. And by this, I can build two sets of families where f is larger than 0 and where f is smaller than 0. The statement holds for both, so let me focus on the positive part. So at time theta, I will define the set A theta as where the time slice, the theta time slice of f is larger or equal than 0. This now partitions my state space at every time, and I have a moving family, a changing family of sets. And this changing family of sets has an escape rate, which is smaller or equal than, or bounded by the real part of my eigenvalue. And since this is now a generator corresponding to a transfer operator, this kappa is going to be always negative, or at least in the closed left-hand complex half plane, and thus the real part is with this minus is less or larger or equal than 0, which means that the escape rate has a upper bound, which means if I find kappa or an eigenpair with an eigenvalue close to 0, then automatically I found a coherent family with a coherence guarantee by this bound. I will not too much get into the details of numerics. I just say it's a hybrid finite volume spectral discretization scheme, which we are using here. It works fairly well. We can talk about it later if you wish. I should point out that this has some connections to evolution semigroups. which is also a very nice theory. It has very strong connections to it. See, for instance, works by Chikon and Latushkin. They wrote a whole book on it.
Sorry, Peter, one question.
Go ahead.
So this is does that matter? Is that for periodic boundary conditions in theta now always, or?
Yes, this theorem is now for periodic boundary conditions in theta. But we are, yes, go ahead.
No, sorry, but in the space you just take these eigenfunctions and then, okay, then you check this property with respect to a theta. So you only have these periodic boundary conditions in theta, and in the space you basically look on the whole space.
Yes, I could do different things in space. What we are doing here is Neumann boundary conditions, homogeneous Neumann boundary conditions, because we are, to be able to do numerics, restricting ourselves to some finite or compact sets in space and take reflecting boundary conditions for the SDE, which then in the operator setting turns into homogeneous Neumann. So we don't lose mass. But we could talk about what happens if we lose mass, then we would take Dirichlet, homogeneous Dirichlet boundary conditions, and much of the theory can be carried over to that case as well.
Sure. Yeah. Thank you.
Sorry. What happens to this when epsilon goes to 0?
Eigenvalues where epsilon goes to 0.
And eigenfunctions.
Yes, yes. Well, absolutely. Very good point. One. So the statement would be that we haven't been considering that for this augmented case, but there are works which consider the epsilon to 0 situation for this forward-backward operation, which I was showing at the beginning. You have to move forward, diffuse, go backward, and that is also by Gary Froiland, where he then connected this to some so-called dynamic isoperimetric problem, some corrected Cheeger constants and Cheeger inequalities. I don't know whether this rings a bell with you. I could tell you more, but that would probably take us somewhere else. So I'm happy to discuss this afterwards.
My guess is that if I just formally take epsilon equals 0 in this operator, then probably kappa equals 0, eigenfunction with kappa equals 0 will be just characteristic functions of every invariant set. Yes.
That is probably correct, and that's why you are not just considering epsilon going to 0, but what you would do is, or what Gary did in the operator version, is to consider the difference of the identity and the operator for epsilon going to 0. So you're not just taking stuff to 0, but you are kind of looking at the higher order corrections, what's happening there, and that is where the interesting dynamic information is hidden then.
No, that was my question. So we will get anything else if we look for coherent sets? Will we get anything else as like approximations to invariant sets of the system?
You get very specific invariant sets, which are most robust under noisy perturbations.
I see. Okay.
And these are exactly the coherent sets. So yeah, your intuition is correct. Yeah. Okay, but that's like in the higher order terms.
Okay, good. Thank you.
No worries. Okay, let me just give you some very basic intuition on. How long am I talking? Okay. So very basic intuition of how the proof of this. So why does this hold? This whole theorem, how to prove it? The basics are there that the norm of a signed density. Yeah, this F has now positive and negative part. Recall. The norm, if we push it with our transfer operator, which is formally e to the power of t times the generator, decays as our eigenvalue tells us it will decay. And from this, we can move to making claims about the retention probability in the whole family of sets. Yeah, to stay in the family of sets until time t goes to 0, like this. Let me show you just 2 movies where we start some positive and negative mass. Yeah, so think of this ink as the blue is negative mass, the red is positive, and depending on where we start, this positive and negative probability, you see that more or less mixing is happening. On the left-hand side, there's lots of mixing. You see lots of purple. That would be cancellation because positive hits negative, while on the right-hand side, you don't see any purple because there's just too little amount of probability mixing up. And this is exactly what is the intuition behind the proof. This, of course, has to be formalized and some bounds have to be applied. Now, this example is done for a very simple system. It is a double gyre, so 2 counter-rotating gyres in the rectangle which you see there as state space, where the separatrix in the middle between the 2 gyres is periodically moved back and forth. So we are squishing and pulling apart the one gyre and the other periodically like this. And then, okay, so before we jump to the examples, I would like to give you some perspective what now this kind of means. On the right-hand side, we kind of have the augmented setup. On the left-hand side, we have the non-augmented but autonomous setup. So here at the bottom is our object, which we are approaching with the numerics, the augmented generator. This can be connected to eigenfunction one-period transfer operator. This already has here the flavor of some multiplicative ergodic theory and some oscillated splittings for this co-cycle of transfer operators. If these things are something your ears are familiar with, then just take this as a connection. By the way, the red things are which we are showing and the black things are where are existing connections. And then we can go up and say this can be related, of course, to a family of functions with some prescribed decay. So this big lambda is some decay rate, and this eigenvalue here is now going to govern the decay of these functions, these families of functions, and from this we can get to the coherent families. But just as well, we could stay on the augmented and thus the autonomous side of things, going to transfer operators on space-time, giving us escape rate, low escape rate augmented sets. So these would be now sausages, which we can then interpret as families of coherent sets in state space. And now examples. So again, this is this double gyre, which is periodically forced. And you see the 2 topmost eigenfunctions of the space-time generator, of the augmented generator. That's why these things are movies. So as time goes on, I'm showing you time slices as they evolve. Blue is negative, white is positive, and you recall from the theorem that the 0 of these eigenfunctions tell us where to make the cut and where the coherent sets are. So these give us now 2 different coherent families. The one is a wobbly left light separation, and the other coherent family is a wobbly gyre to rest separation. And it is known that that there are gyres, some structures which are invariant, at least under the Poincare map of the non-perturbed, so the deterministic flow. This is a well-studied system, and we pick up the structures as they should be. Here is a numerical simulation, how this looks like in the perturbed case. So I initialize kind of 10,000 points in the left-hand side coherent set. So this was the top eigenfunction. and the resulting coherent family from before. And I apply now the noisy evolution to that. And whenever a trajectory leaves my coherent family, as it is defined by the eigenfunction from the previous slide, I'm drawing it red. And what is lost once stays lost, even if it comes back. So it stays red. And I hope it's sufficiently smooth also in the transmission, such that you can kind of see what numerics does. So most of advective mixing is happening here at the bottom, but noise is such that, of course, at the interface of the two sets, it's spitting out some mass as well. And now I'm checking my theorem quantitatively. I'm counting the number of red points from the previous slide, or actually the number of points staying blue up to some time. Red and blue here doesn't mean the same as before. Red and blue are basically all the same. There are 10 different simulations. And I'm plotting on a semi-logarithmic plot the ratio of points which stay inside the family of sets as we computed it up to that time. And you see that the slope is smaller than the slope which is given by the eigenvalue bound, basically numerically validating our theorem for this example. We can drive this a little bit further, actually. There are complex eigenmodes as well. So the eigenvalue kappa can be complex, and then we can build coherent families from this as well. We have to take the real part of not the eigenfunction itself, but we modulate the eigenfunction by e to the power of imaginary unit times the imaginary part of kappa times t. And recall that we had a periodic forcing to the whole system, which means that this ft is now a tau periodic family. This guy, however, has a different period, this modulation. This is a 2 pi over the imaginary part of kappa period, basically giving us a quasi-periodic or a 2-periodic family of sets, if you wish. So this is how then the evolution of such a real part of this thing would look like, actually giving us a yin-yang type of separation of the gyres left and right. And you see it's not exactly periodic in tau. Tau is 5, I suppose, at this point, or 1. But it has multiple periods. This is, of course, less coherent than the structures I've shown you before, because there is just a larger and more diffused interface where mass can be interchanged between yellow and blue. Okay, what happened? Let me go full screen again. Right. You can still see everything, I suppose.
Yes, we can see it.
Yeah,
Okay. All right. So this was the periodics, I think. Can we do more? Is the next question. Yes, we can. We can also approach the finite-time coherence setting with this. Recall we had this forward-backward evolution shown by this picture, illustrated by this picture. We flow forward, we apply noise and move backward. Actually, we can apply noise continuously during the forward and during the backward evolution as well. And this is what has been considered by Andreas Denner, Oliver Junge, and Daniel Mathis before. And now we lift this into a trajectory-free version, if you wish, because we are not going to simulate anything. We are just setting up, again, an augmented generator problem via reflection. And this reflection we are doing in time. So we have one copy of the system from 0 to tau. Capital T is tau here. That's the blue part. And then just flip everything, time, and copy to actually using the reflection map 2 tau minus t. And since we are moving backwards now, the velocity field gets a minus in front. And then we can wrap this whole thing in horizontally around the cylinder, because we are starting at 0, going to tau, and from tau we're going back to time 0 basically. So again, we get something periodic, and we can apply the theory I was showing you just before to, on the one hand, take and construct a reflected augmented generator G hat, and to state a similar theorem as before. If I take this G hat, this augmented generator on this reflected problem, then the corresponding sub and super level sets of the generator, giving us a family of sets denoted by this boldface A here. Its coherence is then larger by some constant times whatever our eigenvalue kappa tells us that there happens. And I don't know why is this happening. Let's go here again. Right, we can use this for now a different setting. It's a perturbed Bickley jet. So this is a horizontally periodic state space now. So here you only see the state, and if you don't know the system, it has gyre-like structures, 3 at the top, 3 at the bottom, and in the middle, so somewhere here, there is a wobbly jet going. And this is a true finite time problem in the sense that we are having a finite and an end time, and we are computing coherent sets. Here are the 6 most coherent sets, which we isolated from the eigenfunctions. Now I'm not showing you the eigenfunctions, but the isolated structures by something called sparse eigenbasis separation algorithm, SIBA, also by Gary and co-workers. Okay, one step further, and that's kind of going to be the last topic I would like to talk about. It's linear response, or more from the application setting, the manipulation of mixing in systems. The idea is, now that we had the quantitative connection between mixing properties of the system and the eigenvalues of this augmented generator G, we could think of controlling the mixing properties through trying to manipulate the eigenvalues, corresponding eigenfunctions of the generator. So to be more precise, I would like to increase and decrease coherence in my system by changing the drift, so the velocity field, V, to, well, locally first. So there is some U, which is my perturbing vector field, however I implement it in applications, and this delta is something small at the beginning, but we actually managed to crank up delta to quite a large thing and still apply our theory. But okay, how do we do this? First of all, if we would consider the transfer operator, then we would run into problems because there's a nonlinear mapping between the velocity field, which is now a time-space dependent velocity field, and the corresponding operator. Think of it as this is the flow field, and the flow operator, the phi t, is of course nonlinear depending on v, and you would have to solve a so-called variational equation to know how this happens, or if you would like to differentiate your flow with respect to v. So that's why it's nonlinear. On the one hand. On the other hand, the generator is now linearly depending on v. Yeah? This generator was the Fokker-Planck operator, so this is clearly linear in v, which leads us to a very simple optimization problem. if we want to optimize the eigenvalues of kappa, at least locally, with respect to V, at least formally. But as a first step, we have to establish the smoothness of the mappings, which start at the velocity field and lead to those quantities which we would actually like to control if we would like to do some kind of a gradient descent or some, let's say, first order method, which relies on local sensitivity, or to put it differently, Frechet differentiability. So that's what we did recently. We established Frechet differentiability of objects from the velocity field space, which is V. It's some properly defined Sobolev space, to the transfer operator, the augmented transfer operator as well, as a function of V. Then also the eigenvalues of this operator, as long as they are isolated. But since this is going to be a sufficiently compact operator, let's put it this way, those eigenvalues which we are interested in are going to be isolated. So there we have Frechet differentiability as well. Also from isolated eigenvalues of the corresponding augmented generator. That's what we are interested in. And also the eigenvectors or eigenfunctions of this generator, as long as, again, kappa is isolated. So with all this armed, we can we? I will try to go to the next slide, right? We can set up a machinery which allows us to measure quantitatively the influence of some drift change to the generator, and through that also through the change of the eigenvalues. And here's the linear relationship, how under this delta parameter the eigenvalue changes. We will need right and left eigenvectors of this generator, or we have to compute functions of the generator and its adjoint, and this is the usual L2 scalar product here. I should mention that we are not restricted to one-dimensional parameter variations. We can actually do the theory for infinite dimensional variations, perturbations as well. So we can choose our perturbing function from, if we want, a infinite dimensional subspace of the space of velocity fields. Here's an example, again, the double gyre system. The original flow would show after some fixed time. This is everything on finite time now. So at the end of times, if I start with points in the right hand side plane, they are blue and red just to indicate where the gyre in the middle is. So these blue and red points are now deterministically evolved by the flow. You see that some stuff is coming to the left, the gyre stays intact. But now if I apply the machinery to increase coherence, I get a velocity field which indeed increases coherence, because there are less trajectories injected to the left-hand side, because I was trying to increase coherence between the left and right separation. And also I can decrease coherence, so I can destroy coherence not just of the left and right separation, you see more stuff is coming up, but also less coherence of this gyre core itself. There you see that the red part is more torn apart. All right, this is the end where we are going with this. We would like to extend this, of course, to other settings, robotic driving, for instance, and use it in different applications, we are starting to develop some more flexible numerical algorithms to do these things, and so on and so on. So at this point, many thanks to my collaborators, Gary Freuland, Han-Cheng Li, and Martin Stan, of course, to funding agencies as usually, and I'm just flashing here a couple of papers which are related to this part of my research, in case you're interested. Many thanks for your kind attention, and I'm looking forward to answering questions.
All right, thank you very much. Any questions?
You have estimates from above on escape rate. Do you have estimates from below?
No estimates from below.
Because of course, the meaning. What I want to understand is, you can, if a kappa is small, then you can identify these eigenfunctions with small as with coherent structures. But maybe there are coherent structures which have nothing to do with eigenfunctions of this operator. Probably not, but for that one needs some estimates from below or something like that.
Exactly. So I'm not claiming that I'm catching everything which is there, but I'm claiming that those which are found, I can guarantee have a coherence guarantee, and for that this bound is the interesting one. With this.
Yeah, of course. Yeah. But in your examples, there is no other coherent structures, which means that probably you capture everything. The question is.
Yes, I suppose I do, and it was a long time ago when I thought about this. In periodic case, if there would be anything, I think I should pick it up, but I'm wondering whether I can give you a good reason for why this is the case. I suppose. So the periodic case is as close as I can get to something which is essentially autonomous in the sense of, Poincare return maps or slices. So in that case, I'm expecting to have anything which is coherent but is not showing up, because if there would be some non-periodic structure, or at least non-quasi-periodic structure, then they would be somehow, well, in the operator sense or setting perpendicular to these nice and slowly decaying eigenspaces, and would decay faster. And from this, I could probably deduce that they have a lot less coherence than others. But admittedly, I'm waving my hands at this point.
Yeah, maybe related to that, actually, Peter, I was also about to ask when this bound becomes sharp. Sorry, I'm sorry.
It's okay. I understood.
So there might be cases where this kappa is actually exactly the rate of escape, exactly, right? I mean, for example, if you look at sets where you use machinery of quasi-stationary distributions, and you take absorbing boundary conditions of these at certain sets, then the escape rates from these sets will be exactly these eigenvalues kappa. And I'm just wondering what would be the situation in your setting now where you can actually find this kind of equality.
I suppose this eigenvalue arises in such a way that it kind of massages together all the information of this escape, or of time infinitesimal escape, for all the time slices. I'm having like different dynamics at different times because it's a non-autonomous problem. So I suppose it's a mixture. I have to kind of, if I would now try to think in a very dynamical or physical dynamical way, you know, I would need to care for how quick is the decay of a time slice. Like if I would freeze my velocity field at some time point, what would be the escape rate there? And also, how quickly am I changing my coherent set boundaries? Because that somehow interacts with that in a nonlinear way. So I suppose if you have the same escape from all kind of families of the time slices, then this bound would be sharp. But this way, since things are changing, the geometry is changing and the dynamics is changing, I get a non-trivial coupling of these things. And this is what the non-sharpness is generated by.
Okay. Okay, thank you.
No worries.
Hello. So I guess the challenge there is that
A lot of feedback now with you and Maximilian.
Oh.
Excuse
Sorry.
Yes.
Was there someone else? Can I ask something?
Yeah, I'm not sure what this. Yeah,
Go ahead.
Go ahead.
So just wanted to say that I guess that's the difficulty that you can't. It's difficult to even define where those boundaries go. But I was wondering, like when you do this